All right, everyone. Good morning. Welcome to session 3 of the Legion School. So today we're going to be talking in some more detail about some of the different operation classes that actually go through the pipeline of the Legion runtime. Do you recall last time we went into a lot of detail about that generic operation class and sort of talked through the semantics of how it works and the different interface that it provides for implementing operations inside of Legion. And today what I want to do is actually look at some more concrete examples of operations that we've actually implemented for doing different things inside of Legion. And so what we're going to do today is we're actually going to start and walk through one of the simple operations all the way from the point where the runtime API calls in from an application, and we'll follow an operation all the way through this pipeline and just see how it works. And then after that, I'm going to give a brief overview of some of the other kinds of operations, and then we're going to look at a second operation, which is a little bit more complicated, maybe not quite in as much detail, but in a little bit, in at least a little more depth. Okay, so the operation that I want to work through first to start, just to show people, how simple it is to implement one of these operations, how it works in the pipeline, is the inline mapping operation. So looking at the Legion interface, we have an operation called inline mappings. So if I search for inline launcher, which is the name, actually I should probably start with, here we go. We have these inline launcher objects, which are used to launch what we call inline mapping operations. And these inline mapping operations serve a very simple purpose, which is if you want to get a physical instance for a logical region inside of a task, these inline mapping operations are how you do it. Effectively, it's a way to say, I want a copy of this logical region here that I can actually access right now. And I wasn't, thinking ahead, so I didn't pass it as arguments to my task, but I need to do it now, and so I'm going to launch an inline mapping operation to get one of these tasks. So the inline launchers here are very simple. We pass in a region requirement for the region we want. We give a mapper that's going to handle the mapper queries for doing this mapping, and we give a tag and so forth. But these inline launchers are really very simple. And if we search for where we launch these, I think if we say launch in, maybe I'll have to do this the hard way because I can't remember what the name of the call is, or is it? Oh, it's map inline is what it is. There we go, map inline. So we have this map. Well, I guess that's the mapper call. Sorry about that. Let's search for inline launcher. Here we go, map region. This is the runtime call that we pass. We want to do one of these mapping operations. So what we do is we pass in our context and our inline launcher, and we'll give back the region that will say, this is the region that we can actually access to actually get access to the data inside of the logical region that we passed in our requirement for in the inline launcher. Let's actually go see where this map region call goes into the runtime and how we start about launching this inline mapping operation inside the runtime. So I'm going to jump back to our file directory. So if we look at legion.cc, let me find it here, just to trace everyone through everything that's going on. And I can't find legion.cc because I'm blind. There we go. So if we search for map region, we see that we just turn around and call the internal runtime, our internal runtime object. Remember, we have one of these per node to ask it to do the inline mapping. So if we jump back and we go into runtime.cc, we will find our call to map region. Here's our call to map region. We're getting our context, we're getting our inline launcher, and we're passing back our physical region to return. So the first thing you'll see is that the first thing we are going to do is, in order to actually kick off this operation, is we're going to call this get available map op. And this is a runtime method on the high level on this runtime class. It's a member method. And what it's doing is the high level runtime maintains a pool of different kind of operations that we pull from whenever we need to do an operation. So for example, we keep a pool of these map ops, which we're going to look at in detail today, that represent the operation, the actual objects that are going to be used to run through this pipeline to actually perform the mapping operations. So the high-level runtime maintains a pool of these, and we recycle them for reasons that we'll see, in a later class, involving not having to prune different operations out of some data structures. But effectively, we keep a pool of these and we recycle them. And so whenever we need a new one, we call this get available map op. And just to show you some of the pools, if we actually jump back to runtime.h, which defines our high-level runtime, and we find this get available map op, you'll see that there's a whole bunch of tasks like this. So there's get available individual task, point task, index task, slice task, remote task, inline task, map op, copy op, fence op. We have pools for all the different kinds of operations that we might ever possibly need to actually get in order to actually perform an operation. And you'll see right below here, there's actually the corresponding operations for returning these operations back to the runtime. So once you're done with an operation, you can pass it back to the runtime, and the runtime will put it back on the queue of operations that are operation objects that are free and available to be used by other people. So effectively, there's just the high-level runtime is just maintaining pools of these operations that we can pull from, and then put ourselves back on to when we're done. And we're going to see that the map op. We'll see how the map op adds itself back to the list of free map ops using this call right here in just a little while. Okay, so let's jump back to runtime.cc. So we know where get available map op comes from. So we search for get available map op. Did I go too far? I went a little too far. Let's see. We want map region. Searching for map region. Okay, we are back here in our map region call. This is where we get our mapping operation from. So map op, if we actually look at it, actually let me show you the declaration of map op. It is in the Legion ops class. So we're in Legion ops.h. If we search for class map op, here's our declaration of the class map op. And you'll see that it extends from two things. One is a publicly visible structure from the Legion interface, which is the inline structure, which we use for handling, which has all the types of fields that are going to need to be accessed by a Legion mapper. The inline class just provides a bunch of fields for mapping for mappers to actually access. And then you see the other thing we extend is the operation class, which we talked in a lot of detail about last week. So when we extend this operation class, that means we override some of the virtual methods. So you see we've implemented activate and deactivate, and we've overridden two of our trigger messages from last week, which are trigger dependence analysis and trigger execution. And we'll look at those in more detail. Before we go into more details of MapOp, I just want to jump back and show you where this inline class comes from, so you can tie it back to how it relates to the Legion.h interface. So if we jump back here and we actually go look at Legion.h, and we're going to search for class inline. There we go. And we'll see that this has a very simple interface for the mappers to access. Effectively, all it is it extends this general mappable interface, which means you have to implement some of these virtual methods here that any mappable object needs to have. And then we have just two really member data fields. One is the region requirement that was requested as part of this mapping operation. And then, we also have reference to our parent task, just so that, the mapper can look at which context we're in when it's doing its mapping decisions. And then to show you just where this inline class gets used, if we search for map inline, this is a virtual method inside of the mapper interface. So if I were to scroll up here, way up here, keep going up, and you see that we're inside here of class mapper. So this is the generic mapper interface. So this map inline call is the mapping interface call that will be invoked in order to decide where we want to create the physical instance for this logical region. You see we pass in an inline operation to the mapper. So we want our map op to extend this inline class so that when we call the mapping interface, all the right fields will be available for the mapper to see. Okay, let's jump back. We're actually going to go look, jump back to runtime.cc so we can go see what we do after we've allocated that map op operation. So we're going to go back to what was it? Map region. Okay, we are back here. So we've got our map op. We're ready to fill in all of its data, and then we're going to launch it off into the Legion pipeline. You'll notice that there are two different variations of filling in this mapping op, one in debug mode and one in not debug mode. The debug mode one calls initialize. They both end up calling this initialize method, which we'll go look at in just a minute. And we pass in different things. The debug one will actually see if you've asked the high-level runtime to dynamically check all of your privileges. If you've said yes, then we will actually go and check the privileges. In the non-debug mode, we will never check your privileges for you because it's a very intensive computation, and we would prefer not to do it in our optimized mode. We also have a logging call here inside of our debug mode in order to report stuff like the logical region that we're accessing inside of our region requirements and the tasks that we're running in and so forth. Okay, so let's actually go look at this initialize method so we can actually see what the map op is doing inside of this initialize method. Let's jump back here. We're going to go to legionops.cc, which is where our implementation of the mapper op class is. So if we search for map op, initialize, here we are inside of the initialize method. So the first thing we do is there's a base class for initializing an operation. So we call initialize operation to initialize all of our base fields from the operation class. We pass in our context. We true saying we want our parent context to track us. We'll go into more detail about why we want to have our parent context track us later. This no event here is effectively just saying that this mapping operation is not going to have any sub operations that's going to launch off, and therefore we don't need to worry about waiting for any of our sub operations to map. We'll talk more about what this kind of event, the all children mapped event means in the future. We save that we mark that our parent task is the same as our context. So this is one of the details of the Legion runtime, which is the context type that we pass around inside of the Legion API is actually just a type def for a single task pointer. So single task is just our enclosing task context, the task that we're running inside of. So to the Legion API, this context type is very opaque, but to us, we can actually see what it is, and we know that it's a single task. And so we know that our parent task is the same as this context. So our parent task is a member field of the mapop class. It's actually a member field of the operation class, and we're just marking that this is our parent task. We have a nice little warning here that checks to see if we've left, we haven't specified any privileges for our region requirement. This is a very common mistake that people make, so we've got warnings for it all over the place. We copy into our requirement. So our map op has a requirement member that is effectively just a region requirement. And what we're doing is we're copying the region requirement from the launcher object over into our local member requirement. And we have a special method that does this for us called copy without mapping info. So region requirements have a whole bunch of other fields on them associated with storing mapping decisions and so forth. That will probably get fixed in the future, but for right now, it's just how the API works. And so in order to avoid copying a whole bunch of fields that we're not actually going to need, we have this special method, copy without mapping info. So we copy over the important parts of the region requirement, like the logical region and the privileges and the coherence. But we don't copy over any of the fields that touch the mapping decisions for the region requirement. We have after we've copied it over, we can initialize the mapping fields. We have some checks here for dealing with special cases like simultaneous coherence and checking for restricted cases. I'm not going to go into detail on those today. We copy over our mapper ID, our mapper tag. This is actually a duplicate statement. We'll probably be removing this. Clearly, we have it twice here. Always good to look at your code again. What we do, we create a special user event for tracking what will be the termination event. This will be the point where the mapping operation actually releases the physical instance that it's made. So we have to create a little termination event that we use for saying when we're done actually touching this physical instance that we're going to create as part of this mapping up. We create a physical region, which is going to be the result of our computation that we're going to fill in as we go through and actually run this mapping operation through the pipeline. We'll go into more detail about what these physical regions actually look like internally a little bit later. Probably not today, but actually in a later class. If we want to, we can check our privileges. So what this will do is actually go and talk to our enclosing parent task and say, check to see if the privileges that we're requesting on this logical region actually meet with the privileges that the parent task has privileges on. So we can dynamically check that property of the Legion program model at runtime if we want to. we are going to initialize some paths and things that we're not going to talk about today. And then we have got a whole bunch of logging calls. But eventually, we're done, we can return this physical region that we created right here, which is going to be the result of our computation. One important detail is that, physical regions, if you've used the Legion API before, if you've done an inline mapping, you're going to have, that you have to actually wait for these physical regions to be valid. And the thing that we're going to do is we're actually going to chain together, we're going to mark that this physical region is not going to be actually ready until this completion event. So every operation from the operation class has a completion event that says when that operation is completed. And by passing in this completion event for our map op into this physical region, what we're going to say is this physical region will not be ready until this map op has gone all the way through the mapping pipeline and actually map actually finished initializing this physical region with all the information about what it needs to actually be ready. So by passing in our completion op to this physical region, we know that this physical region won't actually be ready until we've run through the whole pipeline and done all our stuff. Okay, so we return our physical region, which is going to go back to this call inside of runtime.cc where we were initially coming into from the API. So we're going to jump back to map region. Okay, so and you'll notice what we get back is we get back the physical region result. That's the result of our mapping operation. And eventually you'll see down here at the bottom of this method, we return the result, this physical region back out. So this physical region flows back out to our application. That's how our application gets back the name for the physical region that they know they're going to need that they actually requested for doing this inline mapping operation. Okay, let's look at some of the other things that are actually going on inside of this task. So we have some checks for seeing if we're going to have conflicts with other inline mappings that are going on inside of our parent task. We're going to ignore most of those for today. If we do, we report them with a nice error message saying, why we had an inline conflict, and that could, result in deadlock. Effectively, these kinds of cases occur if someone tries to inline map the same region twice. We don't actually handle that case, so we give you this nice error message. Most people will never ever encounter this because they don't do that sophisticated inline mappings. They pretty much just use them as a way to get access to data when they need it in non-performance important cases. Okay, so after we've gotten through some of those checks for looking for deadlock, one thing we do is we register ourselves with our parent to know that this is an inline mapping that's been done inside of this parent task. This is how we can do the conflict checks that we do up here because we know that our parent task knows about us. And once we've done all that, we can now go ahead and add ourselves to the dependence queue. So we can add ourselves to the dependence queue for the processor of our parent task that we're running on, and we pass ourselves in the map operation as the entry to the dependence as the entry to the dependence analysis. One important thing that you can do here, one thing you'll see in these high-level runtime, in this runtime.cc class, just to point it out, is we have a mechanism for enabling in-order execution of a Legion program. This is useful for debugging purposes. You'll see this pound ifdef in order in a lot of places in runtime.cc. And effectively, what we can do is, in most cases, effectively what we've done is asynchronously launch this map op into our task pipeline, and we returned a physical region that says when it's going to be done, and we know that physical region won't be ready until that completion event that we looked at has actually triggered, which will only happen after our map op has progressed all the way through the operation pipeline. So this whole call is effectively asynchronous. But this in-order execution ifdef here says, if we actually want to see things happen in program order, we can actually force our application to actually pause and wait until our map op has progressed all the way through the pipeline. And so if we're doing, in-order execution, we can actually say we want to wait until the physical region here is actually valid, which means that completion event has triggered, which means that our map op has progressed all the way through the operation pipeline. So this in-order execution is one of the macros that we expose in the legion.h header file, and it's a way to force the application to actually execute in order. But you'll see by default, this in-order execution is not specified inside of our makefile, so we usually don't run this code. Usually we just asynchronously launch off this map op, and we return the physical region representing when the actual physical region will be ready. Okay, so last week we went and looked at add dependence queue, or add to dependence queue, and we tracked how the operation flowed through the processor managers and made it all the way back out through the operation class and called trigger dependence analysis. So let's actually go find trigger dependence analysis for this map op. So I'm jumping back. We're going to go look at legionops.cc, which is where our map op implementation is. So if we search for map op trigger dependence analysis, here we are. Okay, the trigger dependence analysis for this map op is very simple. We've got a bunch of logging calls here inside of ifdefs. You can just ignore those. Really, the main part of this dependence analysis is right here. So what you see is we do three things. As with all operations, we call begin dependence analysis, which you'll recall from last week is a operation is a member method of the operation class. So we say we're about to begin our dependence analysis that sets some of the the internal state of the operation class. What we then do is we're going to actually have to run our region requirement through the logical dependence analysis to see what other operations we depend on. And so I'm not going to dive into this call today because it's a very complex call and it goes and walks the region tree. But what you'll notice is that this runtime pointer here is a pointer to our high-level runtime object. Every operation has a pointer to the runtime. And what we know is that every runtime has an instance of a region tree forest, which I haven't talked about yet. But you can think of it as just the region tree forest as one data structure that represents all of our knowledge about the region tree on the local node for a Legion runtime. And we'll look in much more detail at this runtime, at this region tree forest a little later. But really, all we're going to do is we're going to call this method that says perform dependence analysis, which is going to walk through the logical region tree and figure out what other operations we depend on based on our region requirement that we have asked for privileges on. So really, this call is just going to go walk the region tree and actually do the dependence analysis with operations that have come before us in the same context as our parent task. And so that's where we pass in that parent context, gate context. And so I won't dive into this call today, but we will definitely be looking at it in the future to sort of give some so that you guys can understand how it actually works. Okay, and once we're done, once we've registered all our dependencies, we've registered mapping operations on operations that have come before us, and so forth. We can then call end dependence analysis, which you'll remember from last week, effectively decrements a bunch of the guard reference counters that we had, and may end up triggering the mapping for this mapping operation. Okay, so that's trigger dependence analysis, and what you'll notice is that we've now finished the first stage of our pipeline. Now, the next interesting thing about this map op is that usually the next trigger operation that comes into an operation class is the trigger mapping method call. And you'll notice that we haven't overridden that class for the map op. And the reason for that is we were just fine with the initial implementation of trigger mapping from the original operation class. So if we search for operation, trigger mapping, you'll remember that all this does is once we've satisfied all of our mapping dependencies, trigger mapping is called. And in this case, what we want to do is add ourselves to the local queue of operations which are ready to map. And our processor map manager will then go tell us when it's safe to map. We looked at this call last week, and nothing special is happening. Really, we're just going to go back through that same path that we looked at last week. We go into our processor manager. We end up getting launched onto one of the utility processors to actually trigger our execution. And at that point, we're actually going to have trigger execution invoked. And you'll notice that trigger execution was one of the mapper calls that we overrode for the map op class. So let's actually go look at that. So if we look for map op, trigger execution, there we go. Here's our trigger execution method for our mapping operation. We have some login calls at the top here. We have a little bit of context that we need to get about our parent task and how we're actually going to do our physical mapping. So trigger dependence analysis was our logical mapping analysis, or a logical dependence analysis based on our region usage. Trigger execution is actually where we're going to do our physical dependence analysis to actually figure out what operations, such as like low-level runtime copies and stuff, we have to issue in order to actually run, and then what is the event going to be that's going to actually say when we're done. So we have to get a little bit of information ready so we can go and do that analysis. We have a special case here for pre-mapping. I'm not going to get into pre-mapping today, but we can definitely, it's one of the things that we have to do. So you may notice that we have again, we invoke a method on the runtime forest to do the pre-mapping. We pass in a bunch of information about our requirement and our parent context and so forth. And this call will go and do the pre-mapping pass. If at any point, if we failed to pre-map or failed to do any operation, we can always return false. So notice that trigger execution returns false. We talked about this last week. It's always possible that you might fail to map. So if you return false, the right thing will happen in the operation pipeline. So if we fail to pre-map, we'll return false. Once we're done pre-mapping, we actually want to do our real mapping. So what we do is we want to compute this a little reference for a physical instance, this mapping ref. This is showing through a little bit from the region tree API. We're going to look at this in more detail later, what these mapping refs are. And what we'll do is, the first thing we do is, if we're ready to actually map our region, so if we're not remapping, this if remap case will happen in the case where the application has already mapped this physical region before and it had unmapped it, now it wants to remap it in the same place. And so in most cases, this will always be a true, remap region will be false, so this will always be a true if statement. And so we'll always want to, actually talk to the mapper and figure out how to do our operation. So this is the first mapping call that we see. And what we do is we actually want to have the mapper fill in the fields about where we want to actually map this inline mapping operation. So figure out, which memory we would like to place the physical instance in for this region requirement that we've requested. And so what we do is we call this method on the runtime, which asks us to go invoke mapper, the map inline mapper call for this operation. So what you'll notice is that we actually pass our processor that we were running on, so that way the mapper or the runtime knows how to route this mapper request to the right mapper object for the corresponding processor. And you'll also notice that we can pass ourselves in here as the inline object, which is going to be having its fields filled in for this mapping operation. And then the mapper, of course, can request that we notify it of the results of this mapping operation. So it returns back a Boolean here saying whether or not to notify the mapper operation, the mapper when we're done performing this mapping operation of the results of the decisions that it made in the mapper call. Okay, so after we've invoked our mapper to actually go and fill in our fields to actually do the mapping, we can then actually ask the region tree forest again to actually perform the mapping. So this is the case where we're actually going to walk the physical region tree to figure out exactly which copies and other operations need to be issued, and then whether or not or what event is going to be responsible for representing when we're actually done. And you'll notice that this call to map physical region returns that one of these mapping refs, which effectively is just a reference to a physical instance in the middle of a runtime and an event saying when that instance will be ready. It's possible that this mapping ref is actually empty when it returns. So it's possible when we do this map physical region call that the region tree traversal fails to actually find or create a physical instance for us. There might not be a space in the memories that we're trying to map into. So it's always possible that this map ref comes back empty. So we have to check for that. If we do, we can mark that we failed to map. We can tell the mapper right here. We can invoke the failed mapping mapper call, pass ourselves in, and say we failed to map, and we mark exactly the requirement that we failed to map on. And again, we can always return false, indicating that we've failed to map at any point inside of this trigger execution method. However, we also have the else case here, which is we may have succeeded to map. In this case, we actually have a physical instance and a runtime. Oh, sorry, else is actually mapping against this remap region class or remap region. This is the case where we already know the physical region that we want to map onto because it already exists. And so we can actually just call remap physical region without having to invoke the mapper because we already have a physical instance we're trying to map onto. Okay, if we've made it down here past this if-else branch, it means that we have a valid mapping ref. So this map ref is valid. Notice in the remap case, we can assert that mapref should always be valid. We already had the physical instance ready, so all we had to do was issue any copies to bring any data up to date and get the event that we were ready to execute. So once we've made it out of this if-else branch, if we've made it this far, we've succeeded at everything we've tried to do. And so we have a valid mapping ref. And at this point, we do our third call to the runtime forest to actually register this mapping ref and actually give us back what we call an instance ref, which actually says that we validated that this is an actual instance. We've registered ourselves as a user of this physical instance inside the region tree forest. And again, we're going to dig into all of these region tree forest methods in much, much more detail. So don't feel bad if I'm describing the high level and you can't exactly see what's going on inside of the region tree forest methods here. We're going to go into these in much, much more detail later. But what you see is we pass in our mapping ref, we pass in our requirement, we pass in some other information to actually do the traversal. And what we do is we also pass in the termination event, which says, this is the event that will trigger when we're actually done using this ref. So our completion event for this operation is tied to when the instance becomes ready. And our termination event is going to be the instant or the event for marking when this physical instance is actually done being used by the enclosing parent task, which is effectively when we unmap the physical region that we've returned. Okay, so we get back our instance ref result. At this point, we've succeeded in mapping. So if our mapper asked us to notify it of the results of the mapping, we can fill in the fields on our requirement that the mapper asked for, and then we can invoke the mapper, telling it to notify it the results of the mapping operation. This will then go and call the mapper class or the mapper object on the right processor, telling it, we succeeded to map, and here are the results. We have a whole bunch of logging calls here for logging all sorts of stuff that can go on. Pretty much anything you see inside these ifdef legion logging, legion prof, legion spy, you can pretty much ignore. Those are all logging calls. They're not doing anything important for correctness. At this point, what we do, we've actually tell our physical region, to actually mark that it's ready, that when it will be done, it needs to trigger this termination event when it gets unmapped. At this point, we can call complete mapping because we've actually finished executing the mapping part of our mapping operation. So we're done with that stage of our pipeline. Mapper operations have a special property, which is we like to commit them early because we can actually figure out if it's, in most cases, it's very difficult to roll back inline mappings because of once you've done an inline mapping, you've effectively polluted the parent task context with information. They can access information in regions, so we don't need to worry about deferring commits the way we do for other operations. So we have a special call for requesting early commit, so we can see it early. Once we're done, testing for this, we actually call complete execution. We've launched all the stuff that we need to do to actually execute this inline mapping. We've got our physical instance that says when our physical region will be ready. And then, if we can commit early, we call trigger commit, and then we can return true that we actually succeeded in mapping. Now you'll notice that we didn't have to override any of the other inline or any of the other operation methods for triggering, because all the rest of them, we just use the base default implementations provided by the base operation class. And so again, this is a very nice part of the API where we don't actually have to override any of the other interesting things. Most of the other operations here inside this map op class are very simple. Just seeing what kind of operation we are, trying to cast us as different kinds. There is a check privileges class, or check privileges method here that actually does the checking of whether or not we meet our parent task's privileges and validates a whole bunch of information about the shape of the privileges or of the region requirement to make sure that we're not accessing or that the user has given us good input. I'm not going to go into detail. This is all just a bunch of error checking code. You can walk through it if you want to in more detail offline, but it's all very, very simple. And that's really the end of the mapping operation class. It's really a pretty simple class and a pretty straightforward thing to walk through using, relying on the other APIs inside of the runtime, like invoking all these operations on the forest and so forth. Okay, does anyone have any questions before I move on from this map op operation class? Actually, let me show one more thing before I move on from this, which is one of the things that we didn't talk about a whole lot of detail last week is the map op, or these activate and deactivate virtual methods, which all operation classes have to implement. So I mentioned that all operations are recycled. So once we're done with them, we get put back into pool of resources that the runtime manages for our class of operation. What the runtime promises is that before it actually runs, it will call this activate method on an operation. And this gives us a chance to initialize all of our fields and to clean anything up from previous iterations. So you'll notice that we can call activate operation, which is the base activate call for our base operation class. And then we mark parent context as null and remap region as false, so we can reinitialize some fields. Similarly, we also we also call the operation class calls this deactivate method after an operation has been committed. Just to show you where that actually happens, let's find where this deactivate call comes from. So if I scroll up here, up in this Legion Ops class, we search for deactivate. I thought it would have been called in here. Yes, here we go. So inside of trigger commit, you notice that we call this deactivate method. So after an operation has been committed, it calls deactivate. So if we look at mapop deactivate, we see that we call the base deactivate operation. So we deactivate all the fields from our base operation class. And then we can clear out some of the fields that we constructed as part of our execution. So we can assign our region back to an empty physical region. This will actually remove a reference onto the physical region we created, which is important for garbage collection purposes. I'll talk about that in more detail later. We clear out our region tree, our privilege and mapping paths. And once we're done, we can free ourselves by passing ourselves back to the runtime. So this is where we call this free map op call that we looked at earlier on the runtime to pass ourselves back as a list to operate. An operation is now free to be put back on the pool of map ops to use for future operations. Let's actually go look at this free map op so we can actually see how it gets freed, and then also the activate call. We'll also see where this activate call gets called at runtime before the operation is ready. So if we go look at runtime.cc, let's search for free map op. Okay, so what you see here is that we get the runtime provides this method for freeing mapping operations. We have a lock here that we protect this available map ops, which is just a deck, a doubly ended queue. What we can do is we can take the lock that protects this queue, and then we push ourselves back onto the queue. Now, the other interesting call to look at is the corresponding call that pops operations off of this queue. So if we search for get available map op, what we see here is that we want to get a new mapping operation to return. So we grab that same operation lock. We look at our doubly ended queue of map ops, check to see if it's empty. If it's not empty, we pop the first one off the front, and then we can remove it from the list. Notice here, if we were unsuccessful because the queue was empty, we have a way of creating new mapping ops, and this is effectively just a wrapper call for new that allows us to trace our memory usage. So this Legion new is just a special wrapper call for calling new, so we can track how many things we've allocated for map ops. We pass ourselves in, so every operation will have a reference to the runtime. But what we do is we get back a new mapping op, which then goes into our pool of resources that we will be managing. At this point, we should have a valid map op operation to pass back. And you'll notice that we call activate no matter what before we actually return this as a new valid map op. This activate call was the one that we were looking at back here in legionops.cc, which, let's see, let me make sure I can find it here. Map op activate. And so that's this call right here where we actually activate this mapping operation, which allows us to fill in all sorts of fields and initialize them before we go ahead and use them again. Okay, so hopefully all that made sense, and you can see how we progress through the pipeline. The mapping operations walk through the operation pipeline just like everything else, and then when they're done, they get returned back to the runtime so that they can be reused. Okay. Does anyone have any more questions about the mapop class before I start talking about some of the other operations in a little higher level of detail?
Mike?
Yeah.
Why is activate not just a no-op if you're always guaranteed to do a deactivate first?
Right. We probably could have merged some of this information together. Well, I guess you always want to do an activate because you always want to initialize your fields. You could have done that. I guess if you did that in the constructor, you could have done that as well, and maybe have turned activate into a no-op, and then moved all these initializations back down into the deactivate. I guess it's just a little bit of extra verbosity that occurred just from the code evolving and not having been cleaned up particularly well.
Okay, but it's not some other weird phase ordering thing going on.
No, there's nothing real fancy or special going on here. I sort of have I've decoupled, maybe the style that I've been using is that the activate calls tend to initialize fields, and the deactivate call tends to release resources that we were consuming as part of our execution. And that allows me just to track everything in two separate places instead of garbling it all together. But that's just a convention, and it's by no means necessary for the correctness of the code. Yeah, I suppose it is important in the deactivate call to always release your resources before you return yourselves back to the list, because you never know the next time you might be touched. But other than that, I think that's probably the only performance bug that you would have to worry about with that. So. Okay. Any other questions? All right. Let's actually go look at some of the other operations that exist inside this Legion Ops class, just to give you a high-level feel for all the different things that extend this operation class and what they do. So if we look in Legion Ops.h, most of the declarations that extend the operation class, with two exceptions that I'll talk about briefly, are in this Legion Ops.h header file. So here's the operation class that we looked at in a lot of detail last week. If I scroll down here a little bit, the next kind of class we have here that extends, actually we just do this. We'll search for classes that extend the operation class publicly. Okay, so we have this predicate operation. So one of the things that you'll see in the Legion runtime is the ability to create predicates. All predicates, that we create are special operations that go through the operation pipeline. They're very, very simple operations. They literally just track Boolean values, but you can create predicates and futures, so they get deferred just like everything else. They might have to wait for a future to be ready to actually execute and so forth. So we can have predicate operations. Our next one is our speculative operations. So you'll see that some of our operations allow you to speculatively execute them, which means you can provide a predicate as a precondition for the actual execution of the op. They may, also be potentially be speculated on based upon what mappers decide to do. So the speculative op class is the base class. You'll notice it has some pure virtual methods here, so it's never speculative op is never an actual instantiated class. It's just a base class or intermediate class that some of our other operations are going to support. We'll speculative op here in just a minute after we're done looking at operations. We have fence ops. There are two types of fence ops that you can pass into the runtime. One is a mapping fence, which effectively says make sure all the operations that came before this fence inside of a task have finished mapping before we map anything afterwards. We'll see an example use. There's an example use of these fence ops inside of some of the tracing code where we actually try to memoize some of the logical dependence analysis. We have frame ops, which are a way of scoping how many outstanding operations we have at a time. So if you've looked at creating frames in order to avoid launching too many tasks at a time, we create frame ops for managing that. We have deletion ops. So every time you delete a region tree, a logical region, or a field, or a index space, or a field space, or a field, all of these things get translated into some kind of deletion op. I guess we can see all the different kinds of deletions that we supply here. And we defer all of these with deletion ops the same way that we defer everything else inside of Legion. So we have deletion ops. Let's see. I guess that here we go. Close ops. These are a special. You'll see the comment here says that close ops are a special internal operation, and effectively they're what we use at the end of tasks to actually copy data back to the original physical instances that the task had mapped. We'll talk more about those when we talk about mapping task operations. But these are one of our internal operations, but they go through the pipeline just the same as everything else. We have must epic ops, which are ways of launching a whole bunch of tasks at the same time. These are really meta ops that allow our tasks to ensure that they're going to execute at the same time. We can talk about those in more detail a little later. And I think that's the last thing that extends directly from operation. The thing that you'll notice is there are actually some classes, some other operations that extend from this speculative op. Let's see. Can I spell this property? Let's see. Let's search for speculative op. Here we go. Okay, so here's an example of a class or an operation that extends from the speculative op class. So we also provide a copy operation, which allows you to copy data from one logical region to another. Now, normally, if these logical regions are in the same region tree, Legion will take care of issuing copies for you. But some cases, you want to actually copy data between two logical regions that are in different region trees. And so, we used to have people writing their own tasks to do these copies, and they were really inefficient. And we said, this is kind of ridiculous. We have our own internal copy infrastructure for moving data between regions already inside of Legion, so why not just provide an explicit operation for doing copies? And so this copy op, it extends the speculative op because it's possible for copies to be predicated. So we extend the speculative op. You notice we also extend the copy operation. This is directly from the legion.h header file, the same way that the map op extended the public inline struct so that the mapper could invoke mapper queries on it. Again, our copy op extends public copy. If we continue searching for speculative op, we'll see that there are two other operations in here that extend speculative op. One is the acquire operation. So acquire is a way of gaining user-level coherence for simultaneously mapped regions. I'm not going to talk about what that means today, but effectively acquires allow you to gain a special kind of coherence on simultaneously mapped regions, and it extends speculative op because acquire ops can be predicated. And then we also have its companion operation, the release op, which releases the coherence that you gained from an acquire op. And again, this one is also speculative because it can also have a predicate passed as part of its execution. Let me briefly point out the other operation classes the other classes that extend operations. So if I jump back here, if we go look at Legion trace.h, we have special optimization that applications can use if they're going to be repetitively executing a bunch of the same series of tasks over and over and over again. We have the begin trace and end trace runtime calls. Let me actually just show you where those are in legion.h so that everyone knows what I'm talking about. So in legion.h, we have begin trace and end trace. And effectively, what these two calls allow you to do is to say, memorize the results of the logical dependence analysis for a whole stream of tasks, because I know I'm going to replay them over and over again, and so I want you to not have to redo the dynamic dependence analysis again and again and again. So in order to support these tracing operations inside of Legion trace.h, we have two other kinds of operations. So if I search for public operation, you'll see that we have a trace capture op here, which is used to mark the end of the first time we go through a trace. We can issue one of these operations, which is going to go and create all the necessary data structures based on the set of operations that came before it inside of the trace. That will actually build up the necessary data structures for doing a trace, but this is a special kind of operation. It goes through the pipeline just like everything else. You notice we only have to extend one of the special kinds of analyses that actually occur inside of this tracing process. And then we have a second kind of operation, which is a trace complete op, which is actually used for all the rest of the times that we run through that trace. Once we've already captured the trace, every time after that, we want to replay the results of the mapping dependence analysis. So we put in one of these trace complete ops at the end of the trace, and that allows us to actually go through and set all the different tracing, or fill in all of our information memoized about the logical dependence analysis for all the operations that came before us. The first time through the trace, we launch a trace capture op, and every time after that, we launch a trace complete op, which will go and actually fill in the trace. You'll notice that this trace complete op actually extends this fence op operation that we saw back in the Legion Ops class. And the reason for that is that we actually want a mapping fence at the end of one of these traces to prevent any operations that come after the trace from missing dependence analyses on operations inside the trace that don't actually register themselves in the logical region tree. So we can extend the fence op to actually be able to automatically get that behavior. So effectively, we've extended the fence op, which itself extended from the operation class. Okay, and now let me point out the other case where we actually extend this operation class, which is a very important one, which is actually in Legion tasks.h here. So you'll notice I didn't talk about tasks at all today, but tasks actually have their own extended class hierarchy that extends from the operation class. So if we look, we have a generic task op. This is also a pure virtual, or has some pure virtual methods. We never actually instantiate a task op. But we extend from the task structure from the legion.h header file for handling mapper queries. And we also extend from the speculative op. So tasks can be predicated just like copies and acquire and releases. So we extend the speculative op, and that extends in its own way from the base operation class. And then task op serves as the root of all the different types of tasks that we have inside of Legion. And what you'll notice is that because we again extended from operation class, all of our tasks are just a special kind of operation that exists inside of the Legion runtime. Since we're running out of time today, I'll just briefly give you a tour of the different kinds of tasks that extend this task op, so you can see the whole type hierarchy while we're progressing through it. So if we look at what extends task op, we search for public task op. Here we go. We'll see that there are two of these. There are two generic kinds of task ops. One is a single task. So these represent tasks that are effectively individual tasks that need to run somewhere inside of the machine, but there's only one instance of these tasks. And then we also have a second kind of task op, which is what we call multitask. This class represents a whole collection of tasks that need to be run, that need to be run somewhere inside of the machine. And now each of these single task and multitask classes you'll see they're both virtual. They have their own pure virtual methods. So again, we can't instantiate either one of single task. I think this is single task right here that I'm scrolling through. Yeah, here we go, single task. It has its own sets of virtual methods as well that we can't, that mark that it's not actually instantiated. There are actually a couple of different instantiations of both single task and multitask. So if we search for instantiations of single task, you'll see that we can have individual tasks. So these are the kind of operations that we create when we launch one task at a time from the Legion API. We have point tasks, which we're going to see a while from now are actually tasks that get instantiated by index-based task launches. So these are going to be the point tasks that we generate inside of an index-based task launch. And then we have some other special kinds of single tasks, like these wrapper tasks that are used for creating remote task contexts and so forth. And those are a lot of detail that I'm not going to get to today. The other thing to look at is if we look at what extends multi-task, you can see we have an index-based task, which is an operation that's going to represent an index-based task launch. So when you launch a whole bunch of tasks from the Legion API using execute index-based, we're going to end up creating one of these a little later. And then the other one is slice task. So for anyone that has actually sliced index-based using the mapping API, these slice task objects are what are going to get created when you actually, after you run through the mapping API to actually break an index-based task down into its set of slice tasks. One thing just to wrap up for today, I want to tie one important detail back to something that we looked at earlier today, which is these single tasks. We search for class single task. These single tasks, whether they're individual tasks or point tasks, are effectively what we have all the methods for tracking information about contexts. Single tasks are what actually get executed. So we actually run tasks on an actual low-level runtime processor. These single tasks are the data structures that capture all the metadata that we need for the task actually executing on an actual processor. And so one of the important things that we'll see, or let me show you this, is if I look in Legion types .h, what you'll see is that there's a type def in here. Let's see if I can find it. Here it is. This type def right here, this type defing single task stars to context is effectively saying that the opaque context that we pass out to the Legion .h API is really just a single task pointer representing the pointer to the object that contains all the metadata for actually doing information, or for containing information for actually executing this task on a particular processor. So if we look at Legion.h, let's see, where did it go? Here it is. If we look at Legion.h and we search for context, you'll see context all over the place especially inside of the Runtime API. Let's actually find, if we search for context in here, we'll see context all over the place. And so while this is an opaque handle to all of our users of Legion, this is really just a single task pointer that points back to our single task object inside of the Legion runtime that knows about the execution of this task. And so we keep it opaque to the users. You'll notice that there's no way to see the single task class declaration from the Legion.h header file. But it means that we can actually, inside of the Legion runtime, we know that every context is a single task pointer that we can then use to actually get information about the task, the enclosing parent task, when we launch sub operations and so forth. Just to show you briefly, like for example, if we look at, if we go back to runtime.cc where we looked at where the map op was launched earlier today, we search for map region. You'll notice that it gets passed in a context here, but we actually know that this context is a single task star, so we can do things like context get unique task ID and so forth. So users can't do this, but once you get inside the runtime, you can know that these contexts are really just single task stars that we can have access to for accessing all sorts of information about the task that we're running within. Okay, so I think I'm out of time for today. If anyone has any questions, I think we have a minute here, but I think I'm done talking today. So any questions? All right, I think we're done for today. Everyone remember, we're not going to meet on Wednesday. I have a conflict and Sean does as well. But we're going to start with our first low-level runtime session on Monday, talking about the low-level runtime. And then I will be back to talk more in detail about the high-level runtime next Wednesday. All right, I think we're done.
Thanks, Mike.